Okay, welcome back here now. Let's talk some more about ceramics. We've gone through three different types of ceramics that occur naturally. There is another, which we'll go into now, and they are called silicates. And they're basically very important because they're based on the element silicon. Here's the periodic table of a beautiful, well-worn book. And I don't know how clear it is to you, but over here, silicon sits within the fourth group. There it is down there, beneath carbon and germanium, tin and lead. And all of these, just a couple of brief notes about the periodic table. I assume you may know this, but if you don't, this will be helpful. The elements are all grouped in order of their electronic configuration, the electrons, the size of their nucleus, which relates to the atomic number, and also to their melting and boiling points and other properties. So across here from the left to the right you can see an increasing number of electrons in the outer shell. Although you can't quite probably see it very clearly over here, if I zoom in a little bit we may be able to get some sort of... no, you can't quite see that, it's not very clear. But you notice that, you will notice anyway if you do look at your own periodic table, you'll notice that the outer shell electrons increase from left to right. So over here there's one electron in the outer shell under lithium in this group, 2 electrons in the outer shell here, 3 over here, 4, 5, 6, 7, and a complete outer shell for the noble gases over here. So as we go across, this carbon, silicon, germanium, tin and lead have 4 electrons in their outer shell. They need another 4 valency electrons in order to complete that outer shell, where they'll be in a very stable position. So they can easily take 4 or lose 4, which puts them in a rather unique condition. Silicon is in that situation. So silicon can either lose or gain electrons fairly easily, which means it can form lots of different possible combinations of electron sharing marriages or bonds with other elements, metals, non-metals, and that makes it very, very useful for us to think about as a naturally occurring element. And its properties are pretty well categorized or catalogued. This book here is the distance education from the Department of Education for Engineering Studies, and has a good diagram here of what silicon looks like when it combines with oxygen. So silicon in the middle, and it's quite a small atom in comparison to oxygen. Oxygen is a lot larger. Oxygen needs 2 electrons to complete its outer shell, and silicon needs 4. So with this, oxygen shares 1 electron with silicon, meaning the oxygen becomes a negative because it has an extra electron, and silicon becomes positive in comparison. You get this shape called a tetrahedron. So it's got 4, basically 4, 1, 2, 3, 4, 5-sided shape, and it forms interesting bonds. So the bonds can become either in a sheet form, as demonstrated here, so you can get a kind of flat sheet of silicon atoms bonding up to oxygen atoms, or it can also take a form of a 3-dimensional shape. So instead of being 2-dimensional like a sheet, it can become 3-dimensional, almost crystalline type shape, repeating itself. And the properties of each of those materials are quite different. So let's have a good look at these silicates. The first one, we'll just write it down here now. These are silicates, again naturally occurring elements, ceramics. Most very common one is silicon dioxide, and this will often tend to move into silicon, a tetrahedral shape with 4 oxygen atoms bonding together. And it becomes, really, because of its tetrahedral shape with silicon and the oxygen atoms here, it becomes, the negative outside, it becomes almost like a negative ion. And it requires other elements to be able to stabilize it, and often those elements will be a metal. And often it'll be aluminium will be involved in that. Okay, so the types of formations can happen with silicates could be orthosilicates. And orthosilicates are a combination of metal ions that bind to the silicon-oxygen tetrahedron. So we'll get metals forming on the edge here and binding up to this tetrahedron that we've described. They're called orthosilicates. The other types are Pyro Silicates. And pyrosilicates happen when oxygen atoms form covalent bonds, sharing electron bonds, with more than one silicon atom. And you can get extra metal atoms also adding into that to neutralize the molecule electrically. So pyrosilicates and orthosilicates, I don't think you need to know quite that level of detail, but it's good for you to know, especially I think the idea of the structure being a sheet structure and being able to have different properties. Obviously the three-dimensional property, as you would guess, would make it a much tougher, harder substance. The sheet property would make it a softer thing, but it would also mean there could be slip planes in between these sheets. And that's in fact what happens with a lot of the clay structures that we have, where water forms in between those slip planes and allows the material to be moldable. Okay. Now, a good example of what can happen when you can get long chains of these silicon tetrahedra forming, or you can have the three-dimensional shapes. So almost like a polymer kind of style of thing, a long chain can form of these tetrahedrons. And a good example of what can happen here is asbestos. Now asbestos, it's almost a form of glass, has a good tensile strength along fibres, but it's an anisotropic material, which means that it doesn't have equal strength properties in every direction. And when it breaks to release very fine fibres. So I'll try and show you what that looks like, although I don't have asbestos, which is not a good idea to show you. But I do have some sheet. This is cement, fibre reinforced cement, fiberglass reinforced cement. Previously they used to use asbestos instead of the glass, the fiberglass, and it was built in such a way that when the sheet broke, lots of these tiny fibres would be released. So I'll try and break off a bit here and show you what would look like on this fibre reinforced cement. So I've broken a little touch off there, and I wonder if you can see, if I hold it up to the light, whether you can see some of the tiny fibres that probably not. Okay, there's tiny little fibres inside that cement there. Not really very clear for you, is it? Okay. So asbestos was released. It had strong tensile properties, and we'll talk about why that is, because ceramics traditionally don't have good tensile properties. Had strong tensile properties, and these tiny little fibres could be released, and they broke along lines, along these silicon line chains, creating very dangerous little things that could be inhaled. You can just see a little fibre there near my finger that can be inhaled, and they would cut through people's lungs and create asbestosis. Very problematic. So, okay, fibre reinforced concrete like this doesn't have the same properties. Now, we talked about silicates. We're on the subject of talking about silicates. What happens is when we have the three-dimensional structures, so these are the three-dimensional silicon oxygen structures, the substance that results, whatever it is, becomes a lattice. And it typically has a high melting point, and it can be used in the areas of refractory use, which means that it could maybe make it made out of special bricks that could be used in melting furnaces where metals are being melted. So the very high melting point created can have that effect and make it useful as a building material in furnaces to resist the heat created by molten metals. So these refractory furnaces, the heat resistance can be up to over 2000 degrees for these silicon oxygen combinations when they're in a three-dimensional lattice like that. Now, also these clays, these silicates that are used in clays, more in the sheet form, have a lot of great uses, and clays can become in lots of forms. The clay, when it's its normal state, so it's occurring in the ground, usually has water involved. So these are clays. They have water involved, and when that water is dried out, the clay becomes hard. Now, depending on the temperature which is applied to the clay, the water can be added and it can be softened again. The water will be reabsorbed and the clay can be reshaped and removed. But if the temperatures reach a certain degree, permanent changes take place in the clays, and that's called firing. So clays can be fired, which means to be heated, or unfired, so just naturally dried. And sun-dried mud brick, for example, is an example of an unfired clay brick used in civil structures, especially in ancient times when high temperatures were expensive and hard to achieve. But fired bricks were also used in ancient times, furnaces were available, and permanent change took place in the structure of the clay when it was fired. Now, the firing process, around about up to 150 degrees Celsius, all the water between each of the plates of silicon and metal oxides would be evaporated and it would become quite hard. So over 150 degrees, so between 150 degrees and 650 degrees, and here we're talking some serious furnace here, water is removed from within the structure, the atomic structure of the clay, and it becomes quite hard, and that's called dehydration. Beyond that, from 550 degrees up to 900 degrees, the metal ions that usually form inside these structures, remember I told you that the silicon oxygen tetrahedron basically ends up being negative because oxygen gains electrons and the silicon is positive in the middle, losing its electrons if it's a bond forming shape, and there's plenty of electrons around the inner shells of the oxygen atom to create an ionic kind of effect to this molecule over here. Then those molecules need metals, and often metals will form and you'll get colours forming inside there as a result of the metals. So when those metals are oxidized, forming a gas or forming an oxide or a rust, they move out of the structure, and you begin to get, this is the stage called oxidation. So we're firing up to 900 degrees. Beyond that, you can fire further, so above 900 degrees we have a stage called vitrification, and vitrification is almost repeating what happens in the earth when the rock is molten. So we get those igneous, sort of hard, glassy kind of shapes, which are amorphous usually, and which means they don't have a structure, and they are very, very non-porous, very brittle and very hard, and that's called vitrification, and that happens over 900 degrees Celsius. So the other thing I guess that happens at vitrification is everything usually solidifies into the one single phase. You don't get different phases occurring inside the clay or the ceramic. Alright, now what uses are they? Well, in different stages, building materials, those uses can come in the following way. So we can have earthenware products. Earthenware products, and they are heated up to, or they're fired I should say rather than heated, between 800 to 950 degrees. I got that right? Yeah, 800 to 950 degrees. And they're around about 8% porosity, so they can still allow water to go through them, and they tend to be used for roof tiles and also for bricks. So if you had a roof tile or a brick, and I have a brick over here, that's been heated around about the 800 to 950 degrees. And we'll talk some more about brick making in the future, but that's one use of earthenware. Now beyond earthenware is stoneware. Stoneware is fired at approximately 1250 degrees Celsius, has a very high vitrification, which you remember is when you get that glassy phase that occurs. So not everything is vitrified, but high vitrification, high proportion of vitrification. Has very good chemical resistance, so it doesn't readily respond to losing its electrons or breaking its molecular structure down with acids or anything else. And also it has very low porosity. So low porosity, and that porosity comes between 1 and 2%. So if you want to contain fluids, you don't want them to escape, stoneware is a good solution for that. Next comes porcelain, and porcelain is fired between 1300 and 1450 degrees. As you can imagine, it's usually a light colour, but it's almost completely vitrified. Right. It has less than 1% porosity, so it doesn't allow water to go through it much at all. It is often used as an electrical insulators. So you'll see it used on power stations or in resistors. And sanitary ware, so where you don't want any trapping of water inside the object, so toilets and so forth. And and very hard, so it's a very brittle, very hard porcelain. Okay, and lastly we've got glazing. Now sometimes you might have an earthenware object like, let's see if I can find one for you. Yeah, over here. Without damaging my hand, because this is a cactus. You might have an earthenware object, and you can see it, so it's only been heated up to around the 800 to 950 degrees, but at the same time you want to reduce its porosity and maybe change its appearance, so you can apply a paste glaze, which would be a silicate form, usually with some colouring pigmentation from metal oxide. Fire it up to the temperatures that are required for vitrification, and then you get an outer form of vitrified glassy called a glaze, and inside you have the earthenware. And that's probably a cheaper version than trying to create something like this out of porcelain, and also retain some of the material properties of the earthenware, which may be desirable for you. For example, you might want some porosity down the bottom, or you might want it to be able to breathe a little bit, but that's a use of glazing. Alright, so beautifies. Now, forming processes for clay bodies, very quickly. We might not have time. I think we'll start off the next stage with, we'll finish here and we'll go part 3, forming processes for clay bodies. We'll talk about bricks and then we'll talk about glasses.